In this video we're going to look at some factors that will affect solubility. So these are things that you can adjust or change, and that will also then affect how much solute will dissolve. One of the things is temperature. So temperature will affect solids, liquids, and gaseous solutes, how much will dissolve into the solution. And this is a solubility curve, so this just tells you at what temperature how much, gram-wise, will dissolve in 100 grams of water. So you notice as the temperature is only 10 degrees, let's pick one, let's pick calcium chloride. At 10 degrees you can get 64, 63 grams to dissolve, but at 20 degrees you can get closer to 80. So in most of these that is true. There are a few cases though where the temperature actually causes you to be able to do less. But in most of them you see that the curve goes up. So most solutes, like I mentioned, will become more soluble if the temperature increases. Again, not for every single one, but for most cases. Now, we can also make what's called a super saturated solution, and if you have ever made or eaten rock candy, this is how this is made. So a super saturated solution contains more solute than what theoretically, from our solubility curve, what it can actually hold. So how this works is we know that there's more grams than what our curve says it will hold, but yet it looks like it's all dissolved. It's not sinking to the bottom. So you can initiate the crystallization by adding what you call a small seed crystal. So it's just a very small piece of more solute to it, and that is going to cause all of the extra solute that is in the solution to kind of clump onto or gravitate toward that seed crystal, so that you get these really cool, like some of these are just really cool formations. And so the excess solute that is already in the solution kind of deposits on the surface of that seed crystal. And this is how you make rock candy with the sugar water. You dissolve more sugar in the water than what it can truly hold, and then you initiate this process. You put a string in it with a little bit of sugar on it, and it kind of gravitates to it. It's pretty cool. Pressure will also affect the solubility, but this is more in gases. So gas solubility will increase as the pressure above your solution increases. So think about when you have a pop, okay, something that's carbonated or under pressure. The carbon dioxide that causes it to be carbonated, it is in the solution. It's dissolved in the, let's say, sugar water, for instance, because most pops are just sugary drinks. When you open up the can and the pressure above your solution changes, it can't hold as much. It's not as much gas is soluble, and so it comes out. It fizzes out, and if you left it open, eventually it would fizz out and it would become what we call flat. So this is called Henry's law. This is where the solubility of a gas in a liquid, like a pop for instance, is directly proportional to its pressure. So directly proportional: when one goes up, the other goes up; one goes down, the other goes down. We remember that from the gas laws. So solubility is the S and P is pressure. And so we're going to do one practice problem here. If the solubility of a gas in water is 0.77 grams per liter, so that's telling you how many grams of the gas will dissolve in a liter of the water, and we know the pressure is 3.5 atmospheres. We want to know what the solubility, same unit, grams per liter, what that would be at 1.0 atmospheres. So I know many people like to set up their work ahead of time, so we know that our first solubility is 0.77 grams per liter, and that is at a certain pressure of 3.5 atmospheres. And we know our our second solubility. It's wanting us to figure that out. What is its solubility? But we know that the pressure changes to 1.0 atmospheres. So this is our equation, and this is set up just like Charles' law or Guy-Lussac's law. We're going to have to do some cross multiplying here. Oh, sorry, I got ahead of myself. So this is P2, and then we can plug in our numbers. if we, okay, so here's our equation, and now we can plug in our numbers. Got a little ahead of myself. And 3.5 atmospheres on the bottom. Keep in mind, you still need to be following numbers and units, plugging things in appropriately. We don't want to get out of that habit. And so we're going to be cross multiplying, and x is going to have 2 significant digits. Every single one of these numbers that we're using has 2 significant. So 0.22 grams per liter. And so what that in essence means is if we reduce our pressure down to the 1.0 atmospheres a lot, okay, 0.77 minus 0.22, so 0.55 grams are going to come out of the solution. So that much gas will leave because it can't dissolve in the liquid.